Swayam Prabha. Digital India. Educated India.
Okay, so before I kind of start, I just want to set baseline on why do you want to even learn about this, right? What do I mean by program execution environment and why I think you should learn about it? So what I would say in nutshell is this is trying to cover what is happening under the hood when a program is running. Okay, and there are obviously multiple components involved here, and today I'll be able to touch only some of them because it's a smaller session. But yeah, the idea is hopefully with this session, it brings enough curiosity in you to figure out how things actually work under the hood. What are the contracts that exist between different parties, compilers, linkers, loaders, and so on? And what do they do? Why they are designed that way? Uh, how does it actually matter, right? And if you're questioning on why you should learn these topics, so first of all, it will make you a better programmer. Okay, so many times you would knowing these things will inherently make you aware of how things execute, and by nature of it, what it means is as you're writing program, you also understand the impact of that program when it actually runs. So if you have to do any performance tuning or any performance analysis and those kind of things, it helps you because you understand the end-to-end view of how your program will actually run, and you know where you should look for from the hotspot point of view, or which components might be creating problems that you are running into, right? And that's where I go into debugging. So a lot of times what ends up happening is if you get some cryptic linker error, or if you get some very cryptic behavior, it's very hard to figure out unless you know the basics of what linker might be doing. And if you know them, you should be able to at least reason about what might be happening wrong with whatever you're trying to do, right? So these two are definite benefits. But more importantly, I think what happens is knowing these basics of how currently systems are built and what all things go into the operating system and the system software that comes with it, it will help you set baseline of what is there already available. And many times when you're working on new processors or new systems, right, it's not that you're doing a lot of new innovative things, but you might have some constraints, or you might have some specific areas where your system is different from the other things. So you will be able to still borrow a lot of ideas which were implemented in some other system that you know of. So for example, if you're familiar a lot with, say, how Linux and x86 processors work together, you might be able to take or at least appreciate the ideas they have and see if you're doing, let's say, work on NVIDIA GPUs, how it is different from these things that you have learned. Can we borrow some of the ideas? Can we take that idea and modify it in some way so that it works in our context? So in many cases, you'll be able to use these ideas to build new systems. Okay. So that's the aim. Essentially, if you learn these topics, I hope it makes you a better programmer. You'll be really good at debugging stuff, especially when you run into cryptic issues, dealing with either linking or some undefined behavior and so on. And hopefully these concepts will also help you aware of various systems that are available and how they work, and appreciate the interesting things that were done in some of them. Okay. Now, as an outline, I'll start with life of program, where I'll just give outline of how the program is seen by system. Then we'll dive into details of linkers. But before that, we have to learn the information that is coming in as input to the linker, which is where we'll spend some time in object files. Then we'll switch gears and start looking at the execution side of things, and then static libraries. And then if time still permits, I would like to cover this, but we'll see. I would at least like to cover up till static libraries. Okay. And feel free to interrupt me anytime and ask questions. I would start taking questions at some boundaries, but if something is not making sense at some point, just feel free to ask that. Okay. So if you look at a program, right? So typically you will write program in a high level language like C, C++, Java, anything. It would get translated into an assembly by compiler, okay? And that would essentially get translated into a binary by the assembler, which would then execute on your processors. So this is a very high level view. But if you look at what actually is happening is something like this, where you have multiple source code files, and there are multiple because you would typically modularize your code into multiple source files, so that it is kind of, you get all the benefits of modularity as well as separate compilation. And all these source files will then get compiled into what I would call as relocatable object files, and we'll dive into details of what these means. But essentially you have bunch of object files that are produced by the compiler from each of this source file. Then you need some way to combine these together, because an individual source file may not be self-sufficient. For example, you might write source code only for few utilities. Yes. Currently, I'm on slide which has a diagram and title life of program.
Maybe I am not able to see this. Is it all right?
Go to the list of people and you can see presentation.
Okay, so I will put. Okay.
Can others see the slides?
Yeah, it is visible. We
No,
just need to pin it.
I also can't see the slide.
You need to pin it. Girish, you can just disable your video for a second, and then that will come, I think.
Okay, let me disable my video.
For a second, then again you can come back, so that people just pin it.
1 second. Wait, how do I stop the video?
Yeah. The button which is below, right?
Are you able to see screen now or still not?
Yes, we are able to see.
Okay.
Yes.
Okay, so let me start. Yeah, so what I was essentially saying is you have essentially source code, which is given to the compiler, which forms the relocatable object files. And here compiler you can consider as compiler plus assembler. So don't take it like it just compiler. And then since you have your source code spread around in files, you need some way to combine it, because typically in one source file, you may have written only one logical unit of code, and you need some way to combine it together, which is the job of linker. And in addition to this, you might be using some libraries to pull in some standard utility functions, which linker would pull in, and it will essentially form an executable, which will actually which can be run and loaded into the memory. But that itself will be given to a loader, which would do the job of actually running it. And loader also has something called as dynamic linker as part of it, which if we get time, we'll dive into. But essentially, it will pull in all the dynamic libraries that might be needed for your program to execute. And this is how your program would actually execute. The upper side of the diagram is what I would call as a compile time stuff. So all of this will typically happen offline before your program runs. And then during the execution time, the loader and the dynamic linker is coming into picture to actually execute your programs. Okay. So let's start diving into some of the details of, so I'm sure you must have learned a bit about compilers so far, in terms of what kind of things compiler would do and so on. You'll probably learn about code generation as well if you have not already done. But beyond that, what happens is what I will try to cover in today's session. Okay, so we'll start with the object files and go from there. So essentially, object file is essentially a file that has machine code and some data which is associated with it. In most cases, the object file that you have is a binary file. And it's not a text or ASCII file, because you would like to have this information stored in a compressed way and in a way that can be easily cross-referenced. So this is typically not an ASCII file. And what contains what is there in the object file, if you think naturally, you had some source program in higher level language and it got translated into a lower level assembly. So object file essentially still holds some way of some representation of the program that you had written and the data that you had written, right? So it still needs that information. In addition, it also has meta information about the program that might be needed for linker and loader. Okay, so typically it has information about what all symbols are defined in this file, what all things are referenced in this file. So for example, if there is a source file which is defining a function foo, then in object file you need some way to say that foo is defined in this file. We might be referencing a function called as printf in our source code. So we need some way to indicate that this object file also needs printf, but it is not part of this object file, right? So all of such metadata, which is information about what your program is defining and versus what it is using, it's kind of captured in the object file. Okay. Now, what forms do object file come in, right? So typically there are three forms in which object files exist. There is something called as a relocatable object file, which is what we were seeing earlier, right? So relocatable object file is the object file that contains code and data, but in a form that can be combined with the other object files, right? So typically relocatable object file will be produced out of one source file, and then multiple relocatable object files can be combined together by the linker, okay? There is something called as executable object file, which is essentially representing the object file that can be directly loaded and run in the system. Okay, so at this stage, your code is already linked together, and it is in a state where it can be loaded in memory and run. There is something called a shared object file, which is used for shared libraries in Linux or DLL on Windows. And if we get to the dynamic linker, we'll study a bit more about this. Okay, so these are the forms in which the object files typically exist. Now, how do you actually represent this information, right? How do you represent what is my code, what is my data, what are my symbols, and so on, right? So there are different formats which are available in which you can actually represent this object file information. There is something called as COF, which stands for Common Object File Format. This was an old object format which was introduced in Unix. There is something called as PE, which stands for Portable Executable, and this is actually derived from the COP object format. Okay, and this is used in Windows. So for example, any .exe files which you see on Windows, they are in this format. So if you understand the PE format, for example, you should be able to understand what is the content of .exe file. Okay, because .exe file is an executable format. And similarly, Windows uses this a derivative of COF for representing its object files, relocatable object files. There is something called as ELF, which stands for Executable and Linkable Format. And this is actually a very popular format, and this is used in variety of systems. So many Unix-like systems like Linux, Solaris, QNX, and so on. NVIDIA CUDA also uses this. Android uses this. If you're a gamer, you might know PlayStation 3, 4, they also use ELF format. And in this session, we'll actually focus on ELF because it's very commonly used format nowadays, and it is very extensible. It has a lot of interesting ideas which we can see in terms of how to represent the information. On Mac, there is something called as Maco, which is a Mac object format. So this is used on the Mac OS. Any questions so far before we dive into the details of ELF? Okay. Now, the way the subsequent session will be is I'll start showing you how the ELF is organized so you understand the information. So whenever you produce any object file, right? So let's say I do gcc-c-m32 sample.c. It produces something called as sample.o. And if I execute a command called as file, so file is a Linux command which tells what is the type of file that is given as input. So you can see that for sample.o, it says that it's a 32-bit ELF It's a relocatable because we have produced it with an option -C, and it is for Intel 80386 and some version information, right? If I drop this -M32 argument, what it means is please compile this program for 64-bit. And the only thing which changes is this says now that this is a 64-bit ELF. It is still relocatable and it is for x86 architecture. Okay, so you can see that the kind of information which is stored in this at a high level, and we'll start diving into the details. There are a variety of tools that are available for you to examine the binaries. As I said, these binary formats, these object files are typically in a binary format. So if you simply open it in an editor, it's not ASCII text which you can read. Okay, so you need some specific tools which can actually be used to read through these formats. And it's not very hard. If you want to build your own reader, once you understand the format, it's not that difficult. Okay, so there is something called as obj dump, which stands for object dump utility. There is something called as nm, which is used for examining symbols and stuff like that. There is something called as readelf, which is elf specific and gives out the information. And for Windows binaries, there is something called as dumpbin. So in this session, we'll mostly focus on the first three tools as they work with elf, and they are also available on Linux. So ELF, as I said, every object file may have three formats, right? It might come in relocatable object, it might be an executable, or it might be a shared object. Now, one good thing about ELF is it's a single format that can represent all these three files. For example, on Windows, they use COF for representing the relocatable files and PE format to represent the executable file. So they have two different formats to represent different kinds of object files. Whereas ELF is designed in a way that it's a single format that can be used to represent all the three things. Okay. Now, what is there in ELF? So essentially, ELF has something called as ELF header, and we'll dive into details of what this means. And all of the data that is present in the ELF is divided into sections. Okay, and sections have some metadata stored in form of section headers. And then there is something called as program header, which we will see later in the slides. And what is ELF is about some way to map these various sections into through section headers and program headers. Okay, so this is how typically your ELF would look. So your relocatable ELF would look something like this, where at the beginning there is ELF header. Okay, then all of the data that is present in your object file is divided into multiple sections. Okay, section 1 to n, and then there is a section header table. And the way mapping works is ELF header gives you some reference to the section header from which you can figure out where is the section header. And each of the section header has information about various sections to tell more about it. Okay. And on the execution side, these sections are combined into something called a segment. And there is something called as program header table, which gives the information. So segment is nothing but collection of sections. And ELF header will have a pointer to program header. And from program header, we can get to various segments. Okay. As of now, if you're not fully understanding this, that's fine. We'll show some demonstrations on how this information is actually captured. But at this point, just think of it this way, that the object file has data in multiple sections. And there are some ways by which I can obtain information about where is each section starting, what is size of the section, and so on. Okay. The ELF header is always at the offset 0. Okay, so every ELF file begins with ELF header, and it contains generic information about the object file. For example, what is the word size? What is the machine for which this ELF was generated? Okay, what is the type of this? Okay, and you can print this information using readelf. So for example, if you compile a program using GCC, and you do readelf-h sample.o, it would print an output something like this, where you can see that there is something called as magic. this is used to indicate that this is a ELF file. So anytime you have a file that begins with 7F, 45, 4C, 46, this is essentially indicate that it's an ELF file. Okay. And if you actually look at this, these are the ASCII values for ELF. Okay. And the class is essentially indicating what type of ELF it is, whether it is 32-bit or 64-bit, whether it was Little Endian, what is the version, what is the machine for which it was produced, and then some information about where the section headers are and so on. Okay, so header is essentially describing the meta information about the entire object file. Okay, now let's look at some sample program and see how the information in program is actually represented. Okay, so I have a sample C code where you can see that there are some global variables, some local variables, function call. So whatever is the code that I'm writing, right, within main or any other function, all of that is put into a section called as .text section. Okay, so the content of .text section is code. Okay, all the variables that I have declared globally, which are initialized, okay, they go into something called as .data section. Okay, so init var and arr3 will go into .data section. There is something called as BSS, which is for global variables that are for uninitialized variables. Okay, and remember, language like C says that if you have uninitialized global variable, it is essentially initialized to 0 by default. Okay, which is why these are uninitialized, and we don't want to save any value, so it essentially saves some space in the object file. And then there is something called as RO data, which is for any read-only data that you may have within your program. So for example, in this particular program, this string output is %d/n. This is an immutable string, okay, because this is a literal string which cannot be modified. So that would go into a read-only data section. Variable X that you are seeing here doesn't really appear in the ELF at all, because variable X is stored in stack, and all the references to X will be replaced with relative to stack pointer. So after you're done with the code generation, there is no reference of X. Okay, but you still need to have some references for these variables which are global, because they might be used in some other object files as well, and so on. Okay, so just to summarize, all the initialized variables go into data section, all the uninitialized variables go into BSS section, all the code goes into text section, any read-only string or any read-only data goes into RO data section. Stack variables don't appear in any section, okay, because they are kind of generated. I mean, their storage is automatically generated on stack when the stack is incremented and decremented. Now, if you have to examine, let's say you have produced the object file, right? And I told you now that the content of text section is actually the code. How do you actually examine it, right? So you can use a utility called as obj dump. And if you do obj dump -d, it essentially shows you the content of text section. And you can see that it actually has the assembly code which was generated for this program. Okay. You can similarly examine content of the .data section using obj dump again, or you can also use readelf. So if you say obj dump --section.data, it would essentially dump that information, and you can actually make out why it has this. So for example, if you, for this program, if you execute these commands, you will see something like 2, which is actually coming from init var. You will see A, which is 10, which is coming from here, then B, which is coming from here, and C, which is coming from here. So what you could make out is the .data section somehow has these values which you had written in your program originally, right? So the information which you wrote in your source program as initializations, this is how it got translated into the object file. All of that information went into the .data section. Okay, so that's how essentially init var will become 2, because the content of dot data section has 2 corresponding to init var. Similarly, you can examine the content of RO data section. And if you do that, where if you simply give section as RO data, you'll see some data, but you will see that the data is, if you actually interpret the ASCII values of it, it is output is %d, which is this part. Okay. So you can, with this, you should have enough things to play around and see how your program is actually getting mapped to the object file. So how is the information that you had written in your source code, how it is getting translated to the ELF. Okay. And now we talked about these sections, right? Now, where do these sections exist, etc., is all provided by something called as a section header table. Okay, so as I said, all of the content in your object file is divided into sections, and each of the section will typically have what is the name of it, what type of section it is, what are the permissions, and so on. And essentially, each section is an unsplittable data. So you can't further break a section, but you can move around sections, and we'll see how that happens when we get to the linker. So now let's look at the section header table for this. Okay, so if you do readelf with -S, you can actually examine the section header table, and you can see that there are various sections that are present in the object file. There is something called as .text, which we already saw, which was a text section. There is .data, BSS, RO data. There are a few other things which we didn't talk about, but essentially, if you look at the fields which are present in the section, right, there is something called as flag, right? And in this case, it is AX, and for RO data, it is A. And if you read these keys, what it means is A means alloc. What it means is that this section will be actually allocated in memory when the binary is loaded. Okay, so RO data will also be allocated. This dot data will also be allocated. BSS will also be allocated. So all the sections that have A flag is the sections that will be loaded into the memory. X is essentially indicating execute. So what it means is that the content of this .text section also has execute flag. That means it contains code. Okay. Whereas in the RO data, you don't have this X. So you cannot execute code stuff which is present in RO data because it has data and not code. Okay. Every section also has size, and you can actually correlate it. For example, for dot data, it is 16 here. Remember, these are hexadecimal numbers. So the reason it is 16 is because you have 4 integers, and that much size got allocated because each integer is 4 bytes. So you have 16 bytes allocated for dot data. Similarly, RO data has size of E, which is 15th, which is actually a string length for this. Okay, so you should be able to start correlating how the information that you have with the various things that exist in the object file, right? Each section also has something called as offset, which is indicating where is the content of that section beginning. So remember what I had mentioned earlier, that the ELF always starts with the header. So the offset 0 of the object file contains header. And then there is a section header, which is telling where the content of various sections is. So for example, this is indicating that the content of data section is starting at offset 78. Okay. Now, if I actually examine it, so for example, there is a command called od, to which I can give sample.o and tell it to give me 16 bytes starting from offset 78. You can see that the content of this is actually content of the data section. Like there is 2, A, B, and C. Okay, so you should be able to now realize that every section has an offset, which is giving the starting pointer where the content actually starts. Okay, and I will be able to examine even the string. Like in this case, the string starts at 88. So if I give that as the data, as the starting point, then it will actually print out the string. Okay, so you now know how is the data represented, where is the data stored within the object file. Okay. Any questions so far? Okay.
But like we cannot use this to look at the assembly code, right? Because like that will be
You can technically, which is what we did here, right? So obj dump dash d, if you think about what it internally must have done, is it looked up the text section within the sample.o using the section header. It looked at what is the offset of text section, and it took that entire content, fed it to the disassembler module, which can decode this. And this is the content essentially 8D4C2404 on x86 means LEA 0x4 ESP-ECX. Okay, so it essentially took this content and run it through a disassembler, which can interpret what this code essentially means.
right. Makes sense. Thank you.
Okay. But yes, you can't just look at the raw bits without knowing the decoding logic. You need
Yeah.
to know how the decoding on a particular architecture would work.
Exactly.
So I have a question. So this for the same example, right? The linker, you were saying that linker is converting the assembly generated to this encoding. Is that right?
No, that is the job of assembler or compiler.
Assembler generates this object file, right?
Correct.
Right. So this is just an encoding of the assembly, right? So
Yes.
logically speaking, every opcode, every operand is given some number and in hex, and that is concatenated to form this encoding. Is that
Correct?
Okay, so a similar thing happens in CPU as well, right? When it executes the program, right? The control unit tries to decode what the instruction is and tries to identify something related to ISA, right? So are these same or it is?
They are same. So it's a contract between the compiler, assembler, and the processor. So every processor, right, has an ISA, right? And simply the textual representation of ISA is not sufficient. The processor also needs to document what is the encoding for various instruction and instruction variants that are present in that architecture. So if you are writing a compiler, so for example, let's say you are writing a compiler for x86, right? And you generate some IR. Now you want to translate it into the final assembly. You could translate it into the textual assembly, but you can't execute that. You have to first translate it into the same encoding that is expected by the architecture. And what happens is when the processor is actually executing the program, it knows how to interpret those bits and it internally decodes what it means. So for example, if in my ISA 100 is the opcode corresponding to add instruction, then the assembler would translate every add into opcode 100, and the processor knows whenever it sees 100, it needs to interpret it as add operation.
Okay.
And this is what I was showing in this particular case, where on x86, this particular code, 8D4C2404, means this instruction. Okay. So for example, push EBP means 55. Okay. And since this is a variable length thing, the decoding is also complicated because the processor needs to figure out how to decode these properly. But that's the ISA design part of it. But every processor needs to give out its ISA and the corresponding encoding. And the assemblers or compilers targeting that particular processor need to know what every instruction's encoding is and produce that in the object file.
Sure.